Okay, so first let me look at a curve and plane. Talked a little bit about this last time at the very end. Okay, so let's first talk about curves in the plane. So we have functions f and g on some interval, say from a to b into r, and they are. I'm assuming that f and g are differentiable. And that the derivative are continuous. Okay. And then I'm thinking about the curve. So gamma here of s is a curve, and it's given by that gamma of s is f of s, comma g of s. And I want to look at the length of this curve, right? So s here is running in the interval from a to b. And so the length, and this is the definition of the length, but then we will justify it. So the length of gamma, so L is equal to the integral from a to b of square root of f prime of s squared plus g prime of s squared ds. Okay. Now, why is this the case? So, why is this a sensible definition? So, suppose that this thing here is f of a, comma g of a. So this is the starting point of the curve. And suppose that the curve looks like this. So here is the end point. And now imagine that you take the interval from a to b and you partition it into a lot of small. So you have this partition of this interval. And then you're looking at, so we have the curve here. This is maybe xi minus 1, and here I have xi. And under the map gamma, this little interval here is mapped maybe into this piece of the curve. Right. Now, this piece of the curve, I will then approximate it by the line segment from here to here, right? So if you do that, then it means that you are looking at, so you have that, you're looking at, right, so you have that, so here you have xi minus 1, here you have xi, and you're looking at the curve on this little interval, and so, and the curve goes from, so the initial point is this, right? That's the image of that point, and the image of this is gamma of xi. Right? And so the line segment from here to here, right? So this is, so the length of this line segment, if you have this point here, so this is gamma of xi minus 1, and this is gamma of xi, then the length here is the vector here, so gamma of xi minus gamma of xi minus 1, the length of this. But this thing here is, right, this is the endpoint, is this, sorry, yeah. And the beginning point is this. So this here, so it's the length of this, but the length of this by Pythagoras is the square of the coordinates and then taking the square root of that. So this is what the length of the line segment here is. Right? And now, but now, like the mean value theorem tells you that this thing here is essentially the derivative at some point in between these two. Right? It actually is equal to, if you will, the derivative at some intermediate point times the length of that little interval. Right? This is this difference here. And likewise, so this is x like this, some intermediate point. And likewise for this, there's some intermediate point times the length here. So this means that this little line segment here, the length of this little line segment is equal to, and you see that when you take this thing here and you square it, then you can factor out, so let me just write it out. So you take this thing here, so it's f prime like this, squared delta xi squared plus, and then g prime squared delta xi squared. Okay? But now you can factor this out, so you can write this as the square root of delta xi squared, and then f prime like this squared plus g prime in this intermediate point squared, right? And this here factor out both of them, and so now you can just, when you take the square root, it actually goes out as this is anyway positive, so it becomes like this. And now the functions g prime and f prime are both continuous. So this thing here is like roughly what it is at one of the endpoints, right? So this here is like roughly equal to, right, like this, and then it's like one endpoint, or you can even take like the, yeah, so it's like an endpoint. And so you see that this thing here now, when you sum up all of these over this partition, and you let the partition, the delta xi goes to 0, then this here is going to converge to the integral from a to b of the square root of f prime of s squared plus g prime of s squared ds, right? So that's why, so you take this little curve, it's parameterized, so you take the curve parameterized by a to b, you're looking at this at a partition, and then on each of these little intervals, you approximate the curve by the line segment, and then you let the refinement, the length of these individual interval goes to 0, then actually this approximation will have a limit, and that limit is this integral, right? And so that's why we define it to be the arc length. Okay, so that's our arc length. And so let's look at an example of this. So we'll look at two examples. Let me first look at the case where f of s is equal to s and g of s is equal to s squared. Then I have that, so then the curve is, so the curve gamma of s is s comma s squared, and f prime of s is equal to 1, and g prime of s is equal to 2s. And so this means that, and let's say that it's parameterized s here from 0 to 1. So then the length here of this curve is the integral from 0 to 1, and then square root, and then you have to take this thing here squared, so that's 1, plus this here 2s squared ds. So this is this integral here, 1 plus 4s squared. So that's the arc length, right? So it's given as this integral. The second example I want to look at about for arc length is if you have the unit circle. So suppose that you have the unit circle. So here you have 1. So this is supposed to be the unit circle. So it's x squared plus y squared equal to 1. It's a unit circle centered at the origin. Okay. Now this means that that if you take a point, right, then y here is, so this here means that y is given in terms of x, with that y squared is equal to 1 minus x squared. And so if you're assuming that you are in this upper where y is positive, so if y here is positive, then you're looking at y equal to square root of 1 minus x squared. So in this part here where y is positive, you have the curve, this part here of the unit circle, this one here, is given by the parameterization gamma of s equal to s and then square root of 1 minus s squared, right? And s here is now running, right, s is the first coordinate, so it's between -1 and 1. So s here is between -1 and 1. Okay. Now suppose that you take some x here, and suppose that you want to look at what is the arc length of this part of the circle, right? Well, then in this case, if you're looking at the arc length of this part of the circle, let's call that arc length theta. So theta here is equal to this part. It's now parametricized like this, but x here is, so this here is, so this is the length of gamma, but now gamma, by now s here is running from x to 1, right? Because x is the first coordinate, and it's running from, the first coordinate is running from x, from this point, right, this here, to 1, right? And so now let's try to calculate this length, or at least write it up as an integral. So if we write it up as an integral, we have that, so in this case, so gamma s is equal to s square root of 1 minus s squared. And so if we define f of s equal to s and g of s equal to square root of 1 minus s squared, then we take f prime, well, that's equal to 1, and g prime, right? So there we use the chain rule. So this is equal to 1 over 2 square root of 1 minus s squared, and then we have to take the derivative of this also. So this is times minus 2 s, like that, right? And so this here is, of course, then equal to the 2 cancels, and you're getting minus s over square root of 1 minus s squared. Okay. And so now, if you're looking at, so f prime squared plus g prime squared, this is equal to f is 1, so this is 1, plus this thing here squared, so this is s squared, and then the denominator squared is just, of course, 1 minus s squared. And we can now put it on a common, with a common denominator, right? And so you see that this is 1 minus s squared, 1 minus s squared, that's how you write 1, and then plus s squared, 1 minus s squared. And so you see that this whole thing is the s squared cancel in the denominator, and so you're getting 1 over 1 minus s squared, right? And so this means that the integral, so this length here, and the length is, so actually we call the length theta, and it will be clear in a minute why I do this. So the length here is then the integral from x to 1, right? And then it is of the square root, right? So it's supposed to be the square root of this thing here. So it's the square root, so if you will, it's 1 square root of 1 minus s squared ds, right? So that's the length, right? But if you think about it, so you have here the unit circle again. What we now calculated was that we take some x here, and then we calculated the length of this piece here, right? Well, that piece is, this here is also this is how you define, this is, if you will, this is the angle. Right, so theta is the angle, right? And so you see that, so theta here is the angle, and x here is, so, and this point here, sorry, this point here is cosine to the angle, comma sine to the angle, right? That's this piece. So this means that x is actually cosine to the angle, right? Okay. So this means that theta here, in terms of x, theta is the inverse function, so it's what's called arc cosine to x, right? So this arc cosine, it means that it's the inverse function. If you take the inverse function on both sides of this, right, then, so if you take the inverse function, so arc cosine, so you get arc cosine to x on this side. On this side, you're getting arc cosine, and then cosine to theta. But these two functions together gives you the identity. So this is just theta. Okay, so in other words, what you have is that arc cosine to x is given as the integral from x to 1 over square root of 1 minus s squared ds. So you have this formula here, which is not so surprising, but anyway, you can get it from this. And so now you can get it. So now the fundamental theorem of calculus, so by the fundamental theorem of calculus, then you have that. So if you have a function that is given like an integral like this, then this thing here is the derivative, right? The one thing that's what the fundamental theorem of calculus say, except you gotta be a little bit careful, because this is if the variable is up here, but now it's down here. Because it's down here, the derivative is minus this. Okay, let me explain that. So you get from the fundamental theorem of calculus, the derivative of this function, I claim, is minus this thing here. Okay, and then this should be evaluated at x. Right? This is the arc cosine at x is equal to like that. Okay, so now let's just see that. So why is this the case? So you take so remember that if you have a function f of x, and this is given as you're integrating from some x, some a to some x, a is fixed, and then you're integrating of a function like this, right? Assuming that the function is nice, etc., then we have that the fundamental theorem of calculus, the derivative of this function is little f, right? But suppose I now switch. So now suppose I now look, so I don't look at this, but I look at suppose that g of x is the integral from x to a. Let's call it x to b, just because we usually have the end point as the last point as b. So suppose that the function is like this. What is the derivative, right? So, but this is just the fundamental theorem of. But you know that one of the rules we had with writing the integral is we can write this one here as so. Here I'm thinking about that the function little f is defined on some interval from a to b. And I can rewrite this thing here in this form here, because I can just think about this thing here as the integral from a to b of f of s. Right, so sorry, let me write it over here. So